Hello everyone, my name is Hengui Du, and I'm honored to present our work accepted at CVPR 2026, titled APPO Attention Guided Perception Policy Optimization for Video Reasoning. This is a joint work from Renmin University of China and Tencent. Here is a brief outline of the presentation. I will walk you through our motivation, the proposed APPO method, and our experimental findings. Recently, reinforcement learning with verifiable rewards, such as the GRPO algorithm used in DeepSeek R1, has achieved remarkable success in large reasoning models. Naturally, researchers are eager to apply this paradigm to multimodal large language models, MLLMs, especially for video tasks. However, video tasks present unique challenges. As shown in the perception reasoning curves on the seed bench R1 and perception test benchmarks, we discovered a crucial insight. For complex video scenarios, simply scaling up the underlying reasoning model is not enough. Instead, enhancing the perception ability is much more important to improve overall performance. There have been several recent works. Some researchers proposed mechanisms to let models look multiple times at images or videos, while others designed stepwise process rewards like in R1VL. However, all of these efforts approach the problem from the perspective of enhancing the model's reasoning capabilities, while overlooking the importance of perception in multimodal scenarios. To solve this, we propose APPO. The APPO algorithm primarily consists of two core steps: attention-guided frame selection and intra-group perception tokens reweighting. Under this framework, the policy model generates multiple responses. We leverage the attention scores to select the most critical frames dynamically, choosing whether to use a hard, soft, or all strategy. These responses are then grouped to optimize the perceptual policy. The essence of our optimization lies in the intra-group perception tokens reweighting. Let me briefly explain the math. First, we calculate the KL divergence of the perception tokens to measure the diversity and variations across different groups. The distance metric is defined as follows. Based on this divergence, we compute a dynamic weight factor. Finally, this weight scales the advantage in our policy loss function. By doing this, APPO effectively guides the model to allocate more learning signals to crucial perceived frames during optimization. We evaluated our method across diverse video benchmarks including Seed Bench R1, Next QA, and MV Bench using Quen 2.5 VL bases. As shown in the tables, compared to supervised fine-tuning, SFT, as well as standard RL methods like GRPO and APPO, our APPO achieves state-of-the-art results. It also outperforms other heavily trained video reasoning models, demonstrating highly effective perception optimization. Why does APPO work so well? When we analyze the training process, comparing APPO with GRPO and APPO, we can see that APPO exhibits higher generation entropy and gradient norm. This indicates that our model maintains a much larger exploration space, preventing early collapse and leading to superior reward scores at the end of training. We also conducted comprehensive ablation studies on hyperparameters, showing robust performance across different network levels and regularization weights. In summary, APPO provides a novel, effective approach to optimizing video perception policies by leveraging attention mechanics and dynamic token reweighting. Thank you for listening. I'm happy to take any questions.